Yeah, thanks guys for coming out. There's a lot of cool talks happening in this 10 a.m. time slot, so yeah, we're thankful you guys came to this one, and we're sure that some people had a late night last night, so thanks for making it to this one. Some quick formalities. Tom's the guy with the beard. I'm the Canadian. Don't hold it against me. We're both pen testers with PSC. PSC specializes in PCI assessments as well, and we also do pen testing in non-PCI contexts. Our day-to-day kind of just involves going through large enterprise organizations and going through various network segments trying to find cardholder data. We're also looking for pen testers, so if you know any or if you're interested in pen testing, either come and see Tom and I after, or Joe over here in the front, and we'll be happy to talk to you. So before we jump into a quick primer, what's Wordsmith? Well, it's just basically a tool which can generate dictionaries. The only thing that we're doing differently is that we are generating dictionaries based on US states and specifically geolocation data. Geolocation data can just basically kind of be boiled down to cities, landmarks, zip codes, area codes, towns, and that sort of thing. We'll get into exact sort of data sets that we're collecting, and we'll also go into some statistics a bit later. But we're taking these word lists and we're just going against and cracking against large hash sets, or just hash sets in general, to identify what sort of passwords people have and if they're introducing geo-based passwords into their phrases. So yeah, we're going to go through a quick primer here of just basic authentication process, as well as the difference between passwords and hashes, and dictionary tags. We've timed it. It should take about 3 minutes. It's about 8 slides in total. For those of you who already know about password attacks and dictionary attacks and hashes and that sort of thing, there's going to be an image on the next slide here. And if you can tweet us the hash type that's in this image, we have some swag that we're giving away. So we've got like Case Logic backpacks and I think phone speaker amplifiers and a single selfie stick for someone who really wants a selfie stick, I guess. So that's our Twitter handles. I think it's also in your brochures. Or go and check out Wordsmith. I just made the repo public, so you can find it there. And I guess just as a quick show of hands, how many pen testers are in this room? Does anyone do pen testing? Joe? couple of guys over there. Great. So if you've ever done any sort of man-in-the-middle attack on your network, and I guess if you're a blue teamer who's ever done a man-in-the-middle attack on your network, this hash type should look pretty familiar to you. So yeah, here it is. You've got kind of a couple seconds here to take a look at that and send us a tweet here at our Twitter handles, and we're happy to give away some swag after. But for now, we'll head back to the primer, and Tom is going to walk you guys through the primer.
Thanks, Sanjiv. So let's talk about a simple authentication process. This is Bob in the extent of my Microsoft Paint skills. Despite what Bob's Prohibition-style hat might suggest, Bob is a user in a Windows environment. And this is Bob logging into a Windows host with a username of Bob. And this might be locally on a workstation. In order to unlock it, this might be remotely via something like RDP. And we've taken the liberty here to unmask the password field, so you can see that Bob's password is password123. On submit, when Bob clicks enter, that input of password123 is put into a one-way hash function. And the output of that is a fixed length character string, which you see represented below. That's what we call a hash. And what's important to note here is that this is a one-way function. We can't reverse this process by putting a hash into the hashing function and retrieving the original clear text password. So after we've hashed the password, we put together Bob's username and password hash, and we send it to the authentication server. This might be locally in a SAM database. If you're joined to a domain, this might be Active Directory domain controllers ntds.dit. This backend database holds, and this is a little bit of an oversimplification, but this backend database holds a listing of all the users and their password hashes. So we're not storing passwords in clear text here. And from there, we basically just do a lookup of Bob's supplied credentials. We find the record for Bob, and we match the supplied password hash with the stored one. If it's correct, we allow the login. If it's incorrect, we'll bump up the failed login count and deny the login. So we can't reverse this hashing process. So how do we convert a hash back to its original string? The answer is there's no direct way. But what we do have are a very particular set of words. Words that make password cracking a nightmare for hashes like these. And particularly we use a dictionary attack. So what are dictionaries? They're simply just large list of words, usually grouped together by some type of theme. So they might come from password breaches like LinkedIn or Yahoo or Adobe. There's also great word lists out on the internet that you can find for free, like Rockyou, Top 10K. There's even some paid ones like Uniq. Despite its price tag, Uniq is a password list that any pen tester or auditor should have in their toolkit. So in order to carry out a dictionary attack, first we need a few prereqs. First is a solid dictionary or a good word list. Second thing we need to know is the hash type. So in this case with Bob, we're using NT hashes or NTLM. If you're authenticating against a Unix or a Linux type server, it's going to be some variation of MD5 or SHA-1, usually with a salt. The third thing that we need are a list of password hashes. These are usually exfiltrated from compromised systems, maybe like a local Windows workstation or an Active Directory domain controller. And these are what we're doing the lookups against. So the steps for actually carrying out a dictionary attack boil down to this three-step process we call the guess, encrypt, compare cycle. Our guesses are words that we're plucking from the word list, and we iterate through them one by one. From there, we take the input word and we put it into our encryption algorithm, in this case, an NT hashing algorithm, and it gets outputted this fixed length string. Then we take that hash and we do a lookup against our list of obtained password hashes. If they match, then we know we can map that back to the original word that we guessed, and we have our clear text password. And Sanjiv will move on to Wordsmith.
Yeah. So as we mentioned briefly at the beginning of the presentation, Wordsmith is just a word list generation tool for US states and I guess geolocation-based data. So what kind of geodata is in a word list? Well, we've got things like cities and towns. We also have landmarks. So in Nevada, you're going to have Area 51, things like the Hoover Dam, that sort of thing. We've got streets and roads. We have zip codes, sport teams, colleges, common names, and area codes. Now, why geolocation data? Well, it's really interesting. I guess it's kind of a marriage between curiosity and password analytics and just general human behavior. I remember I was testing, I was an internal penetration test for a client in a very small state. And as part of my post-exploitation process, I tend to go from system to system and scrape credentials out of memory, just using Kiwi or Mimikatz or something like that. And that usually enables me to collect a large amount of passwords to then enable me to move into another network segment or access applications which unlock greater depth into that environment. Now, collecting all these passwords, I realized a common trend for several of these users, and that's I couldn't crack these because these are specific geolocation-based passwords that weren't going to exist in any sort of password list that's currently out there. Things like sport team names or colleges or other things that might be related to geolocation. So I thought to myself, well, it'd be pretty neat if someone put together a word list generation tool, and then that kind of transformed to, well, we'll just put together a word list generation tool for geolocation data. And as we'll get into some statistics a bit later, we kind of found out that we've limited some guess, encrypt, compare cycles and been able to actually turn this into something quite useful. So I should probably mention, where's all this data coming from? Well, Wikipedia and the US Census have a ton of this data, and it's readily available to the public. All we've done is we pulled it, scraped it, and put it into nice little phrases and words which appear in word lists. OpenStreetMap is another good source as well. We've also had to put together a collection of data sets for area codes because that was a little harder to parse using our parsing engine, so and required a bit heavier parsing. So we actually have some custom data sets which we made as well. So Tom is going to talk to you about how Wordsmith works, and then we're going to jump into a demo. So yeah, take it away. Cool.
So the GitHub repo is live now. When you do your initial git pull, you'll see these files listed there. On the right, you see the actual Wordsmith Ruby file. There's also next to it the sources.yaml file. It's basically just a simple configuration file for all the internet sources where we're pulling down data. And we broke it out like that to hopefully make it a little easier in a modular design to be open to extension and for easier management of our internet sources. Next to that, you see a data.tar.gz, which is basically just a compressed data archive, where we've already pre-scraped all of the data that we're using for Wordsmith and compressed it there. You'll also find a gem file just to make installation a little bit simpler. And there's a README there, which you'll see in the repo, that'll walk you through some of the dependencies and installation. So when you run Wordsmith for the first time, it's going to do a couple checks for some of its files that are needed. If it doesn't see them, it will unpack that data.tar.gz file and explodes it into the current working directory in a subdirectory called data. That data directory is mostly categorized by state, with the exception of some of the custom data that we've had to massage into place. At the top level, you'll see some of the directory for the area codes, names, which we've pulled from US Census, is first names, last names, baby names, sports, which are mostly big four sports in each state at this point, and then the states themselves. And below that, you see an example for what kind of files you would find in the California directory. So you see a cities.html there, colleges.html, landmarks, roads, zips. These are words very specific to that state. If you notice the .html extension, these are actual HTML source files that we've pulled down from our internet sources. And the reason we've done it like this is because we've added an update option within Wordsmith. It's a -u flag. So sometime down the road, if you'd like to update your data manually, you specify the update flag and it'll actually go out to all the sources and update your local data repository for you. To parse this data, we're using gems like Nokogiri and Spider. Mm-hmm. And we do all these lookups offline, so locally, just for speed performance. So a word list that's been generated by Wordsmith kind of looks like this. And I'm using an example that Sanjiv went through earlier with roads from Nevada, particular Fremont Street. So the word as it comes out of Wordsmith looks like that. It's a capital F. There's a space in there. There's a period at the end. So we added in some just very basic mangling for words. So we can split on spaces and break out Fremont and street into two separate words. We can remove special characters. We can remove spaces. There's also options to convert all of the words to lowercase, if that's your preference. You can also specify a minimum character length. So let's say you've compromised a domain where you know the password policy has a minimum character length of 8. Well, you can specify the minimum length here, and it will truncate all words that are not at least 8 characters in length. And now Sanjiv will take you through the demo.
I've seen some really bad things happen with live demos in the past, so let's hope this all goes well. All right, so is that text? How's that? Can everyone see that? Maybe go a bit bigger. Cool. Okay. So yeah, as Tom mentioned, these are kind of the initial git pull files, and if we just go ahead and run Wordsmith for the first time, you're going to see that all these files get unpacked. There's also a warning message that you see here where it says cool is not found in path. Now that's because I'm running Wordsmith on my OS X system. I don't have cool installed. But if you're running this on Kali or something, it's going to pick that up in your path variable and you'll be able to use cool. Now, the purpose of cool is because we've integrated support for things like domains and in-files. So for those of you who are unfamiliar with cool, basically if you specify a domain name, let's say client.com or facebook.com, it'll go out to that domain and it'll look for unique words and scrape it from that application. And the default cool settings, I think, stays within the scope of that domain name, and it only goes a certain recursive depth and follows any hyperlinks that take you to any other links on that scope. And it'll pull the client's name, it'll pull other unique words and strip out some of the common words like of, the, any connection verbs, things like this. And you can also have an in-file where you specify various client domain names. And all this is just to better populate this word list. So we've integrated support for cool. However, you don't need to use it because we also have some other options. Now, as we kind of mentioned, from a top-down approach, it all starts from a state. And typically, when I generate a Wordsmith word list, I'll use a -all option. And all is going to give me cities, colleges, landmarks, phone numbers, roads, teams, zip codes, and also names. Names. So names would be like common last names, baby names. You have no idea how many times I see a first name or a baby name as part of a password. Yeah, so I guess let's run through an example. So we'll set the state for California, and we'll look at some common sport teams there. So as you can see, these are all of the sport teams in California, and that's just doing a basic lookup on the HTML files that we've already pre-pulled. Now, these are great, but we can also mangle these and get every single permutation of these words. So as you can see here, we've got Sacramento Kings, Sacramento, and somewhere up here, there'll probably be Kings as well. And there's only one instance because there's probably some other teams here which have Kings in their name, but we also do a sort and unique so you don't get duplicate words and things like this. What's also pretty neat is that we do things like zip codes. So we've got every single zip code in Nevada, or landmarks. So if we set the state to DC, we can look at landmarks, and we probably tend to see things like White House or whatever, like the Lafayette Building, things like this. Yeah, and if I guess we set the state to maybe Massachusetts, we can look at some of the colleges that exist there. So these are probably see Harvard or MIT at some point in here. Yeah. So as I mentioned before, these are just some of the options, the singular options that you can set for per state. We can also do multi-state. So for example, CA and Nevada, and grab me all the area codes for those two states. Now this is pretty verbose output. I guess the inverse of that would be quiet output. So let's set the state for California. We're going to grab everything we possibly can, and we're not going to have it as verbose as this. And so you can start seeing some things here of how many landmarks there are, how many zip codes there are, but this isn't really useful because we're not getting any words. So we can go ahead and output this to a file like california.txt, and it'll collect all this data and stick it into a word list for you. But as we kind of mentioned before, these are just the actual words themselves. These aren't the mangled versions. So we can specify the M flag, change that to California mangled. And now you can see that there's a little churning time here for especially the roads, because there's 250,000 roads that we're now going to have to mangle, which now outputs almost double the amount. So like Tom had mentioned earlier, we've split on space, we've concatenated, we've stripped symbols, and things like this. Any other options that anyone wanted to see from this help area, or see if a particular college that someone went to in a state shows up?
Can you compare the number of roads in California versus nationally? I'm wondering how much overlap there is and how much benefit there is to restricting it by state.
Sure. So we also have an option built in here for all, so you can churn through every single state and create a mega word list for everything as well. So that's, yeah, it's totally an option. As you can see, you'll just start spitting out everything's just an array. Mm-hmm. Well, yeah, so but that's with the quiet option. If I remove the quiet, we're going to grab, basically, it's just going to keep on churning like that. Yeah. Yeah. So, sorry, is there another question? Yeah.
I was going to say, how do you account for like local or regional businesses? Do you go ahead and specify the -u option and put in the URL?
That's a great option. Yeah, sorry, it's a great, yeah, so.
Repeat the question?
Sorry, he said, how do you account for local businesses? So the -d flag for the cool integration. So let's say you're testing a particular client. The client, there's probably going to be some password variation in there that's a client name 123, and so that cool integration will scrape that client's web application, pick out that client's name, and put it into this word list for you as well. I don't actually have internet connectivity here because we're at BSides, and I don't want to connect to Wi-Fi, so I can't show you the cool integration aspects of it. But yeah, that's basically what our Wordsmith demo is. And what's really interesting are some statistics that we're going to kind of show you guys. And I think you've heard me talk enough, so let Tom just kick that off.
Cool. Yep. So we wanted to measure how effective geolocation-based word lists were. So to do this, we did a couple of tests. Some of the prereqs for this test, we first built a hash cracking rig locally in our shop, and we got our hands on some real NT hashes. So we grabbed some hashes from actual real-world internal penetration test from clients in Massachusetts, it's a little over 400 hashes. Wisconsin, about 2,000, and New York, which is about 500 hashes. The hash cracking rig itself, our weapon of choice for cracking NT hashes is hashcat. The hardware is fairly modest. It was just an NVIDIA Grid K520. But even with that, we could get about 3 billion guess encrypt compare cycles per second. So we're turning through passwords fairly quickly. And just last week, Sanjiv put a post on his blog for those interested that want to build their own hash cracking rig. And he goes through the process of doing so in Amazon's for doing some advanced work. It's got about 57.
Kind of can be translated into 2011 Active Directory user accounts, which can kind of further be translated into 2011 employees, although that might not necessarily be true because there might be some accounts being shared. So we'll just say 2011 Active Directory user accounts. Now, as Tom had previously mentioned, the top 10K word list is just a collection of the top 10,000 passwords. Things like password, love, God. Anyone who's seen Hackers will get that reference. But yeah, we're taking those 10,000 word lists and we're injecting those individual words into the dead hobo rule set, which is 58,000 rules. So these rules can prepend symbols, append numbers, lowercase words, camel case words. So for every single word, you're doing 58,000 different permutations of that word based on this rule set. So yeah, the 10,000 top passwords took about 2 seconds to run against these rules and uncovered 237 of these organizations' passwords, which means that 237 Active Directory user accounts had a password that was in the top 10,000 word list as a root password in their I guess, password string. Yeah, Rockyou uncovered another 1,094 passwords, which is now at 66% of a cracking success in total of all these hashes. And now our Wisconsin-generated word list took 12 seconds to run and uncovered another 11%. So that's 229 passwords. Now, what should be key here is that this Wisconsin word list is it solely consists of geo-based passwords. So at this point, we've cracked 66% of the passwords, but the additional 229 passwords are all things like cities, sport teams, landmarks, zip codes, and things to that effect. So there's a question over there?
Are they discrete, or would there be duplicates between Rockyou and Top 10?
There would be duplicates. So this is a collective cracking session. It's called, basically your hash cracking pot would be populated with 66% of these passwords at this point, and so it's a collective addition. So yeah, we uncovered another 11% of passwords that were all geocentric. Now, yeah, so if I remember correctly, Wisconsin, some of the really common passwords like Green Bay, Packers, first names and baby names as well. Massachusetts had a smaller hash set, about 400 Active Directory user accounts. That makes top 10K with the 58,000 rules run about a second and recover 52 passwords, which is about an eighth. And that's really surprising because it just goes to show that some organizations have really weak password complexity rules and enforcements. Rockyou recovered a staggering 65% in 24 minutes. And with the dead hobo rule set, and our Wordsmith generated word list, another 56. And again, this is all geo-based word lists, geo-location-based words, which are found after in about 12 seconds. And Massachusetts, I mean, people always use sport teams' names like Red Sox and things like this, but what's really interesting is you'll see a lot of city names as well, like Boston, Boston Marathon, Cambridge, and Harvard, and Fenway for landmarks as well. New York, 552 hashes and 552 Active Directory user accounts. What's really surprising with New York is that 0 were recovered with top 10K, which we can allude to several things here. Either the Active Directory domain controller has a third-party plugin, so this New York organization has imported a list of known compromised passwords or bad passwords into Active Directory through some sort of third-party module, which technically refrains users from creating bad passwords. Or as a non-technical control, they have just great security awareness programs or long and complex password requirements or things like this. That being said, the Rockyou word list, which takes about 26 minutes to run, uncovered about 220 passwords, and our New York Wordsmith generated word list recovered an additional 59. And as you can imagine, some of the popular passwords would be landmarks like Empire, or I think I have some examples here. Yeah, Empire, Broadway. There's also one user in particular who had the state NY abbreviation, and then 5 numbers, which are the zip code, and then a symbol as part of his password. So yeah, Tom's going to kind of summarize that last sort of segment there.
Cool. So some of the conclusions of this. Oh, yep, go ahead.
I was just wondering, did you try the New York data, the New York hashes against the Wisconsin list?
No, we didn't. No.
Because that would be very useful to see whether you're actually getting value from paying attention to geography as opposed to just what's on these lists.
Absolutely.
So you need to do that crosswise.
Sure.
Yeah, so to further extrapolate that, we can also just do all states in general against that New York word list as well. But the real takeaway here was just kind of for that particular state and that guessed encrypt compare cycle. So for one state, it took 22 seconds, but for all states, it might take an hour. Who knows? We haven't actually tried to do that yet. But that's, yeah, great question.
So some of the conclusions from this testing, we got a little bit of confirmation bias here in that we'll get into the psychology of how users choose passwords, but we know that users like to choose passwords that are near and dear to them. They choose passwords off things that they know. The street they grew up on, the name of their child. And that's what we're seeing reflected here in our results. And with that, there's a little bit of a time CPU cycle trade-off in that instead of using a blanket word list and looking for low-hanging fruit, we're spending a little extra time up front to craft a more tailored list. And we're spending less time or less CPU cycles on crunching those less pertinent words. And it's a small sample size here, but with these cases, we cracked at least an additional 11% of passwords in a reasonable amount of time. And I think this speaks a little bit to the relevance of the generated passwords. So next steps for Wordsmith, where we see this going. We're always thinking about data. We have ideas for more. It's difficult to have to actually marry an idea for data and actually find good sources for it. But we like to expand on, say, the sports. We've seen users who love to have their favorite athlete or their favorite player as the base word of a password. Maybe team mascots or names of stadiums. You could include famous people like politicians or actresses or actors. State symbols, things that are very relevant to a state, such as the motto or a state song or state flower. And we've gotten recommendations from the community too. Larry Pesci recommended looking at regional food or cuisine or agriculture. From the design, the co-design perspective, it is modular. We like it to be even more so, just to have it open to extension. We think that this framework could be extended to not only include states, but also to include provinces or territories or even other countries. And we could even change the granularity of how we're looking for this. When Sanjiv and I were concepting Wordsmith, we were thinking about what scale do we want to start with? Do we go as macro as continent, or do we drill down to country, state, city, road, address, actual geo-coordinates? So maybe the future version could, instead of a user inputting a state, they input an address or a pair of coordinates, say 50 miles, and say, give me all the words that Wordsmith can generate in a 50-mile radius. So Sanjiv and I are both believers in free and open source software. We believe that everyone should have access to all the source code at all time. We also believe that we're not the smartest people in this room. So if you guys have any ideas for data, for features, if you have experience with looking at querying APIs for geocentric type data, we would love to talk to you. Please send us a pull request, submit issues, hit us up on Twitter. The repo is listed there. We'd love to share this with you. So with that, this is contact information. Also, if you replied to Sanjiv's hash challenge earlier via Twitter, feel free to hook up with us. We'll either be at the back room or in the passwords, and just bring some verification that it's actually you on the other side of the tweet. But with that, we thank you for coming out and open the floor to questions.
Yeah, thanks guys.